Okay, and we're back at it. So the plan is not to do too many more derivatives. I feel like we did a lot of derivatives, but I did want to work on some of these, just one implicit differentiation one, but then I am planning to move on to maybe just chapter 5. We're going to do integrals. All right, but I do want to work through this one. So, but just delete all this because I don't really know what that's about. All right, so we take the derivative of both sides. We should get, so we're going to get f of g of x, sort of what it really is. But so we're going to get cos xy times xy prime, which is equal to cos xy times, so it's going to be x prime y plus y prime x is equal to, so this becomes 1. So it's just going to be y plus y prime x. Okay, so that's the right-hand side, or left-hand side, sorry. And then the right-hand side is just going to be 2x plus y prime. All right, so you end up with, oh wait, this is not cos. This is going to be, oh no, this is cos, yeah. So we're going to get cos xy times y plus y prime x is equal to 2x plus y prime. Okay, now this is where I just fall flat. I don't even know what you're supposed to do after this. So let's just expand. So we get y cos xy plus y prime x cos xy is equal to 2x plus y prime. So what do? You okay, so we're going to move this term over, and we're going to move this term over. So we're going to get y prime x cos xy plus y prime is equal to 2x minus y cos xy. Okay, so then we can factor out y prime from this, right? So we can get y prime x cos xy plus 1 equal to 2x minus y cos xy. But then we divide, so then we get y prime is equal to 2x minus y cos xy over x cos xy plus 1. Okay, but then is that all you can do? Is that the answer? So maybe, okay, so I guess it's, so I guess it's that you can't always find an explicit. Okay. All right, so it's time to switch over to integration. So we're going to practice integrals, but I also want to skim through. I don't think I'm going to read through all of this, but I am going to skim through the definition of the integral. Okay, so they define the area of a region. Let me read this. Why not? Okay, there's the picture. I mean, okay, all right, so that's good. I don't think we're gonna do these problems, but I do want to do chapter 2. Let me look at the review problems in here. Yeah, because like the squeeze theorem, there was something yesterday that used the squeeze theorem, and I don't remember. Okay, yeah. So some of this stuff on computing limits would be good to know. Yeah, exactly. Okay, find the limit. All right, so really we should do this now. Okay. Okay, yeah. So this is the most important thing. because I feel like we're going to be applying this definition a lot. But we also want to know about the indefinite integral. Okay, so the definite so if f defined on AB divide AB into delta x is equal to b minus a over n. X0 is equal to a, x n equal to b, x1 star, xn star in each subdivision. Then we get the integral from a to b, f of x dx. So this is all just syntax, right? Is equal to the limit, as n goes to infinity, the sum from 1 to n, f of xi star delta x. So that's just the rectangles. The precise meaning of the limit means for every epsilon greater than 0, there's an integer n. Right. Oh, this is very cool. Yes. This is the delta epsilon type thing. It's basically saying that n allows you to control the difference between the actual value and anyways, it just says that it converges. The sum that occurs in definition 2 is called a Riemann sum. This is actually interesting. Coming back to a subject like this is actually really fun because it's like, look, only a finite number of jump discontinuities. Suppose that you have that, what was that Dedekind set where you have Q is equal to 1 and R and all the irrational numbers are equal to 0, and then it's going to jump, densely everywhere. Okay, so wait, what is the definition of integrable? The definition of integral, but where is integrable? Do they define? Should we go through this thing? I mean, we get, when you see let omega be an open set in the Euclidean space and f from omega to the complex be a Lebesgue measurable function. I don't think so, guys. It's just a little bit above what we're doing right now. Okay, let's not do that. I think it just means that it's continuous, right? Oh, wait, hold on. Oh, okay. Wait, so we missed a part that's important. Okay, if the limit exists and gives the same value for all possible sample point choices, then f is integrable. All right, very good. So that's important. All right, now we can move on. If f is integrable, what does this mean? Okay, so this, they're just asking you to turn it into, but okay, on the interval. So they're just, okay, so this is just a syntax rewriting, which is fine. Okay, so they don't, we're still all indefinite, but now let's get to the indefinite. All right, they're just saying that the midpoint is a better approximation. This is more of a numerical thing, but we're not going to be, okay, properties of the definite integral. Okay, that's cool. That's cool. Linearity, this is cool. This is these 2 and 3 are actually really cool because it shows that the integration function is actually a linear transformation in some vector space. I guess it's on the, I don't know what it is, but this is specifically for definite, but it holds for indefinite. So let's okay, give us a couple of inequalities. That's nice. All right, so that was actually a good review, and I liked it. But we want to go to, all right, the fundamental theorem of calculus, and I need to go back and get and look because I missed a problem on the quiz that allowed me to simplify based on the fundamental theorem of calculus. I mean, it's actually really cool. The fundamental theorem of calculus is appropriately named because it establishes a connection between the two branches of calculus, differential and integral. Differential calculus arose from the tangent problem, whereas integral calculus arose from a seemingly unrelated problem, the area problem. Newton's mentor discovered that these two problems are actually closely related. He realized that differentiation and integration are inverse processes. I mean, that's got to be mind-blowing, dude, to actually realize that, because we're just told that, and then you kind of sit with it and you just take it for granted. But when you think about these guys actually discovering this stuff, it's pretty nuts. The FTC gives the precise inverse relationship between the derivative and the integral. It was Newton and Leibniz who exploited this relationship and used it to develop calculus into a systematic mathematical method. In particular, they saw that the fundamental theorem enabled them to compute areas and integrals very easily without having to compute them as limits of sums. The first part of the fundamental theorem deals with functions defined by an equation of the form where f is a continuous function on AB, and x varies between A and B. Yeah, this is a good picture. Observe that g depends only on x. Which appears as the variable upper limit in the integral. If x is fixed number, then the integral is a definite number. If we let x vary, then the number also varies and defines a function denoted by g of x. If x happens to be a positive function, then g of x can be interpreted as the area under the graph from a to x. The area so far. Yeah, this is the picture that I was imagining, which is good. If f is the function whose graph is shown in figure 2, oh. These ones are easy. G of 3 becomes hard because I don't know what that function is. How would you know that? So does the area under the graph of f from x to x plus h? Mm-hmm. Okay, yeah. All right, so FTC part 1. Yeah, I'll be right back. Okay. So since this is continuous Okay, I think I get it. Yeah. So but it doesn't actually matter um so what is it called again in the definite integral? What do they call it? The the bounds. Oh, okay, yeah. So okay, that clarifies a big confusion that I had. Hey, what's going on, bro? I don't have wait. No, I have Plus. I don't have Pro. Pro is like $200 a month, dude. I can't afford that. That's insane. Okay, yeah. So um okay, yeah. So you're gonna end up with seek x. Oh wait. Yeah. This becomes u. So you end up with seek u times du dx, which is equal to seek x to the fourth times 4x to the third. All right. Okay, cool. Yeah, see, this is the kind of stuff that I need practice with. All right, then FTC part 2. If f is continuous on AB, f is continuous on AB, then the definite integral from a to b of f of x dx is equal to f of a minus, or f of b minus f of a for any f is antiderivative of little f prime equal to little f. Okay, cool. So that's the big thing. Right, so how do they want you to do this? All right. The integral from 1 to 3 of e to the x dx. So we know that e to the x prime is equal to e to the x. So therefore f is equal to e to the x. So then, and this is f of x really. So then big F of 3 minus big F 1 is going to be equal to e cubed minus e. All right. Nice. This is actually going pretty well. Okay, so in this section they give you the fundamental theorem and then they start to show you examples of antiderivatives, but they don't actually give you techniques of finding integrals until chapter 7, I guess. Or maybe they probably do it in 5.4 as well. Okay, great. Okay, so this is it restated. All right, f is continuous, right? Little f is continuous. Then if g of x is equal to the integral from some constant to x of the function f of t dt, and remember that's just the limit of the sums. We just went over that. Then the derivative of g with respect to x is equal to the is just equal to f of x. And then the definite integral. Okay, cool. I'm not going to do... So, I mean, we could do this. I don't know how they expect you to do stuff like this. Like, you just have to guess, I guess, because they haven't introduced any of this. Okay, let's see. Okay, indefinite integrals. We saw in 5.3 that the second part of the fundamental theorem of calculus provides a very powerful method for evaluating the definite integral of a function, assuming we can find the antiderivative. In this section, we introduce a notation for antiderivatives, review the formulas for antiderivatives, and use them to evaluate definite integrals. We also reformulate FTC2 in a way that makes it easier to apply to sign. Okay. All right, so the indefinite integral is you remove the bounds, and because this is ambiguous, I guess that's why we do this. Yeah. Right. Oh, and here we go. Oh my goodness. So the linearity ones are like really important. I want to spend some more time on this non-E exponentials because it's actually very cool. This I will always forget, man. I don't know. With the practice, I actually am feeling a little bit more confident with this stuff. These, I don't know. You just gotta memorize them, I guess. But it's like, I'm not gonna memorize those. Not yet. The memorization will happen in doing the problems. There was a use substitution one in there that was really tough. In my quiz. I think we're probably gonna do the chapter review one. So let's just hop over to here. Right. So whenever you have a function that was like, okay, it's like that. This isn't exactly a chain rule because then f would be prime, but oh, but that is what it is. Yeah, it's all about getting out of the chain rule. That's a kind of strange footnote, actually. Bro, the way that the patterns of these trig functions are nuts. No, I didn't know about this. Where does the 1/2 come from? Oh, dx equals 1/2 du. All right. All right. It's time to get crazy, man. Ooh, let's do some true false. I'm down to do some true false. All right. True false. If f and g are continuous on AB, then that is true. Okay, so I'm just going to write these down just so that I can test them. 1, true. 2, that's not true. Just take f of x equal to x and g of x equal to x. So they're both the identity. So then you get x squared here. So it's x cubed over 3. But then this gives you x to the 4th over 4. So no. So that's false. 3. That's true. 4. That's false. 5. That's false. That looks true. 7. F and g are continuous, and f of x is greater than g of x for all x in a and b, a to b, then that is true. If f and g are differentiable and f of x is greater than g of x, then f prime of x is greater than g prime of x. I don't think that's true. consider like we can delete all this stuff. Oh my gosh, can I just whatever. I hate these stupid animations. These user interface design are so ridiculous. So consider cos x plus 1 and consider cos x. So, oh wait. So this one's going to be minus sine of x, right? So there are places where this is, and this is going to be cos x, right? So anyways, the point is that this is, so this is f prime is minus sine, g is sine, g prime is cos. There are points when g prime is above f prime, so that's not true. So that 8 is false. All right. I don't know how to do this one. Is this like some even odd thing? I don't know. All continuous functions have derivatives. I want to know more about that. I'm almost positive the answer is no, but right. Okay. All continuous functions have antiderivatives. Okay, so 11. Wait. So I skipped those two, so we're just going to go to 11. That's false. 12. Okay, that. Okay, that makes sense though. I mean, if you think about like absolute value, you can the Riemann sums will definitely converge. That is false. I'm just skipping all the ones that look like I need to compute something. Oh wait, 0 to 3. Oh, 13 is true, I think. This is 15 is false. 14 is false. 15 is false. 16. Yes, the 16 is true. 17. I don't care. 18. Yes, 18 is true. Let's do the first 5. All right, so I got true, false, true, false, false. True, false. True, false, false. Okay, good. Well, let's see what they're. Yeah, see, this is the exact example that I did. All right, cool. So, let's do. If f prime is continuous on 1 to 3, then the definite integral. I said 6 is true. Okay, 6 true. 7 true. 8 false. Skip 9 and 10. 11 is false. 12 is true. Okay, cool. 13 true. 14 false. 15 false. 16 false. 17, 18. Wait, 18. Oh, okay, wait. 18. Oh, because no. It's because you can have a finite number of jumps. False. You can have a finite number of jumps. You just can't have an infinite number of jumps. Because then you can just piecewise do it, I guess. All right. Well, that was good. Now let's yeah. Wait, what? Oh, maybe we should do these. All right, we're gonna do 43 through 48, but then we're gonna try to get to chapter 7 where it has all the tricks, like integration by parts. Oh, some of these are indefinite. Or we'll do the indefinite ones of these maybe. All right, let's just jump into it. I don't know why I'm like hesitating. All right. All right, time to just jump into some integrals, man. I'm gonna do this. Make it a little bit easier for me. All right, so how the hell am I gonna do this? Damn, I don't even know how to do this one. Oh, okay. Wait, let's plot this function. Let's see, what does this look like? 1 minus x divided by x squared. Pretty weird function. All right, so okay, so what they actually, instead of doing this, what you're supposed to do is you rewrite this into 1 over x minus 1 squared. And then I think you can probably just do this. So let's just rewrite this as like this, and 1 over x minus 1. So then you can integrate all of this separately by the linearity property of the integral. Is it not this? Let's see, let me double check my answer. Minus 1 over x minus 2 ln x plus x. Okay, cool. So we did it with some help. All right, 25. I'm only doing the indefinites so far. X plus 2 over square root x squared plus 4x. Oh, hey, how's it going, Carlos? All right, so what's going on here? Wait, this is a 4. All right, so this is a chain rule. So f is equal to f of x is equal to x to the 1/2. G of x is equal to x squared plus 4x. And I believe that we can pull this one, so this is equal to 1/4 d dx x squared plus 4x to the 1/2. So then all we have to do is do this. So we're gonna get f prime of g of x times g prime of x. So this is g prime is equal to 2x plus 4, and f prime is equal to 1 over 2 root x. So we're gonna get 1 over 2 times x squared plus 4x to the 1/2 times 2x plus 4, and then this is all 1/4. So then we get x plus 2 there's a weird I think something happened here. Oh, you know why? This is actually a 2 because you're going to be dividing by 1/2, which is multiplying by 2, so then this cancels, so this is not even there. So then you so then this is not there. So then you get finally x plus 2 over x squared plus 4x to the 1/2. Cool. All right. All right, more integrals. You know what I think you're supposed to do? I think you're supposed to say u is equal to 1 plus cot. Because I think, okay, so cotangent, I'll never ever stop doing this. This is always what I do. So cotangent is going to be a over b. Okay, so, but it's also, that means that it's going to be cos over sine. Because that's equal to a over c times b over c. Wait. C over b is equal to a over b. Okay, great. So this is sine over cos. So u is equal to 1 plus sine over cos. And I'm pretty sure, so now we can just do f prime g minus g prime f over g squared. And that gives us, so this is equal to f over g. So f is sine. So we're going to get cos times g. So this is cos squared. That's going to be plus sine squared over cos squared. This is going to be 1 over cos squared. Oh, what? Wait, but maybe we can still simplify that because so this is, oh, you know what? Actually, I got it. We're chilling. Wait, are we chilling? There's got to be a simplification here. So sec squared, so du dx is equal to secant squared x. So then So then cos squared du x du is equal to dx. So then the idea is that we have this integral, we have cosecant squared x over u times cos squared x du. And then there's got to be something here, right? Because this is going to be like 1 over sine squared times cos squared. And this becomes this becomes cot squared. But now you just have cot squared x over u du, but that doesn't help you at all. Let's see what we can do here. Okay, wait. How did I get this wrong? Wait, cotangent is... Oh my god. No, cotangent is cos over sine. So you actually get f prime, which is minus sine. You get minus sine times sine, right? Because minus. So you're gonna get you're gonna get minus 1 over sine squared, right? Okay, so then this does cancel. So then and then this is, because this is, okay, let's just take a step back. Okay, so we have du dx is equal to cosecant squared x. So then du over cosecant squared x is equal to dx. So then we get this integral of cosecant squared x over u times du over cosecant squared x. Then we get this. Then we get ln. See that bug? Okay, we get ln of 1 plus cot x plus c. Oh yeah, minus. All right. This is going to be okay. I don't know how you got this messed up, but that's okay. Yo, what's up? All right, we're back at it. More calculus. Man, I really want to get back to doing some fun stuff. I mean, calculus is fun, but let's be real, it's like not super exciting. It's mainly just because I've done it before, I think. All right. Sine of x times cos of x. All right, let's think about this one. Um, I believe that this is going to be it's just sine. Let's double check. Let's double check, man. Let's double check. All these are just use subs. We gotta get back to the we gotta go to some of the harder ones, man. I gotta practice integration by parts. That's really what I gotta need to practice. Okay, we got it. That was correct. Alright, what are we on now? We're on 29. The integral of e to the square root x over square root x. Alright, this should be... If we let u equal e to the root x, then we're going to get du dx is equal to... that's not exactly what we want, because then we get du over... Yeah, we don't want that. But if we did u is equal to square root x, du dx equal to... Yeah, that's what we want. Wait, is it? Because then what we're going to get is we're going to get do we have to do... I don't think we have to do this substitution, though. I think we can leave it as root x. But I don't know if you're allowed to do this. Oh yeah, you can... Well, oh yeah, because you could just... Oh. Because what you can do is that you could also rewrite this as 2u du equals dx. And then, yeah, so you can do that. That's fine. Okay, so what are we on? I feel like these are all u subs. All right, but let's just do one more or something. This is the integral of cos of ln of x over x dx. So if we were to let u equal ln x, then we're going to get x du equals dx. Then it just becomes integral of cos u du equal to sine of ln of x. But I do like to look at what these look like. I'm not going to switch the scene, but I am just going to do it myself. Cos of ln of x. Pretty crazy looking graph. All right. So this is my solution. All right, that's correct. So we can just all right, why not? Why don't I just... tan x ln cos x dx. Tan x ln cos x. It doesn't even look that cool, man. All right. Tan x ln cos x. So I'm wondering maybe if you let... Okay, so dx tan is going to be, since it's s over... This is equal to secant squared, right? So if you let u equal cos, you're gonna get a du over minus sine equals dx, but then all you're gonna get is a tan over. Then you're gonna get a sine over cos times ln u times du over minus sine, and then this just goes like that, and then you're left with ln of u over cos x du, which is like not that much better at all. But alternatively, um I mean, but if you take tan x as u, I mean, that's not going to work. And you can't take, I don't know how to do it. This one's kind of hard. Because if tan x, then you're just going to get ln of cos x, u ln cos x over, well, this is going to be like over secant squared x. Bro, what? This is saying do integration by parts. We haven't even learned that yet. Alright, so we're not going to do 31. Ooh, okay, 32 is clever. Alright, we'll do 32. Let's see, 33. Yeah. Okay, so I think we can do all of these. This one's 34 is going to be hard. All right. All right, so 32 is important though, because 32, I really wouldn't know how to do that one. So we have x over 1 minus x to the 4th to the 1/2. So if you take u equal to, obviously taking u equal to this whole thing is not going to work because it's not going to cancel enough stuff. But if you take u equal to x squared, then we get du over 2x equals dx. So then we get, let's just pull the 1/2 out of here. Du over x, these cancel. Then you just get, let's just do the square root. 1 minus u squared. So now we're trying to take the integral of 1 over square root 1 minus u squared du over 2. But the thing about that is, right, I'm pretty sure the way that we did y is equal to arc sine x. So then you get sine y equals x. Then you get cos y prime is equal to 1. Then you get y prime is 1 over cos y. Then you get, wait, this does not seem right at all. I totally forgot how to do this. Oh, wait, what? Oh, because the only way that we can rewrite it is, you don't do this, but you say that cos y must be equal to 1 minus sine squared y to the 1/2. So then you have, okay, so then you have this identity to rewrite. So then you can, all right, so then we get 1 over 1 minus u, 1 minus x squared to the 1/2. Because cos y, so you replace this with this, then you get this, but then you replace this with this, so then you get 1 minus x squared 1/2. So then we know we're going to get 1/2 a sine x squared plus c. Wow, that's a pretty brutal one. All right, I think that this one might be pretty easy. All right, integral x cubed over 1 plus x to the fourth dx. So we take u equal to 1 plus x to the fourth du over 4x third is equal to dx. So then we're going to get 1/4 the integral x over u times du over x third. So then we're just going to get ln of 1 plus x to the fourth over 4 plus c, like that. All right, that one was pretty fast. All right, this one is going to be weird because it's one of these hyperbolic trig functions, which are pretty weird. Hyperbolic trig functions always mess with me. All right, so we have, all right, so we're doing the integral of sine h 1 plus 4x. All right, so to do this, we're definitely going to do a u sub. So we're going to get du over 4 is equal to dx, letting u equal to 1 plus 4x. Then we're going to get 1/4 integral sine h of u du. But the problem here is I always forget this, and I don't know how I'm going to remember it. But I think sine h of x is equal to e to the x minus, I can't remember which one's plus and which one's minus, e to the minus x over 2. I think it might be 2. Let me look up hyperbolic trig functions. Yeah, so that was right, but like I don't know how to memorize that. So then so presumably we can take this and split it out into 1/2 integral e to the x dx. All right, so let's do that. So we're going to do 1/4. It's going to be the integral e to the x over 2 dx minus the integral of e to the minus x over 2. So we can pull 1/2 out of this whole thing just by rewriting the definition, right? So we're going to get 1/8 integral e to the u du minus integral of e to the minus u du. So this is just going to be, and this 1/8 is on everything. So then we're going to get so I'm pretty sure that this is going to be 1/8 e to the u. And then the integral of this is what? Well, if we think about it, d u e to the minus u is equal to minus e to the minus u. So then presumably that's also the integral. So I'm pretty sure that this is going to be plus 1/8 e to the minus. So I'm pretty sure that this is just going to be yeah, 1/4. Oh, okay, so this is gonna be 1/4 cosh u plus c, which is equal to 1/4 times cosh 1 plus 4x plus c. I think that that's right. Nice. All right, that was correct. All right, the next one is I feel like I'm all right. Well, let's just crush the rest of these. Why not? How hard is it? Sec x tan x over 1 plus sec x dx. Okay, I'm pretty sure what we're gonna do is let u equal to 1 plus sec x, because yeah, because if we have a 1 over cos, then a 1 over cos, if we have we're gonna give g prime f over g squared, which is gonna be minus sine. Well, and this is a minus, so this is gonna be sine over cos squared, which is equal to, we could write it as, well, so this is gonna be du dx, right? And so what we're gonna get is we're gonna get tan cos, because if you invert this, you're gonna get cos squared over sine. Oh, it's gonna be cot cos. And I think, oh, and this is sick actually, because so yeah, so we're gonna have du over cot cos wait a minute is equal to dx, but then we're gonna have sec tan u du over cot cos. We could also keep it as so wait, this is gonna be sine cos. So we could also write it as cos squared du over sine. All right. So all right. So we got some issues here. So seek. I mean, you could write this as cos. Well, why do I? You know what? Hold on. So tan is sine over cos. Then we have a 1 over cos times this. So we have a sine over cos squared. Okay, all over u times cos squared sine. I hate these because I never. All right, so what we want 1 over u times sine cos squared times cos squared sine. This all cancels. This is du. So then, yes, we get ln 1 plus sec x plus c. It just took a little bit of massaging the trig functions. Okay. Let me check if I'm right. Yep, ln 1 plus sec theta. All right. This one's going to be 1 plus tan t is u. Then you're going to get du dx is equal to sec squared. So then over sec squared, this cancels. Then you're just left with u cubed. So you're going to get u to the fourth over 4. But you got to go back. And so you're going to get 1 plus tan t to the 4 over 4. Oh, and then they reevaluate the bounds from the substitution to make that easier. All right, I think we should hop back over to the textbook because we just did a bunch of integrals. All right, I think we want to just hop into chapter 7. All right, so we got this one, we got this one. Yep. Yep. All of these are pretty standard stuff. Maybe except for these arcsine, arctan ones. Those are probably the hardest ones for me. In this chapter, we develop techniques for using these basic integration formulas to obtain for more complicated functions. We learn the most important method of integration, the substitution rule. The other general technique, integration by parts, is presented in 7.1. We then learn methods that are special to particular classes of functions, such as trig and rational. Integration is not as straightforward as differentiation. There are no rules that absolutely guarantee obtaining an indefinite integral of a function. Okay. Every differentiation rule has a corresponding integration rule. For instance, the substitution rule for integration corresponds to the chain rule. Yeah. The rule that corresponds to the product rule is called the rule for integration by parts. The product rule states that if f and g are differentiable, then their derivative of the product is equal to our standard rule. In the notation for indefinite integrals, this equation becomes Oh, that's pretty clever. Okay, so into by parts. If you start with d dx f g, you get f prime g plus g prime f. Then integral of f g prime plus g f prime dx is equal to f of x g of x. We can yeah, I mean, I totally don't remember this derivation. It's actually really cool. G of x f prime of x dx. Where's this dv coming from? It is perhaps easier to remember. Okay, so let u equal f of x, v equal to g of x. Then du is equal to f prime dx. dv is equal to g prime of x dx. Oh, so if we have f g prime dx, then this becomes u. So dv is equal to dv over g prime of x is equal to dx. So then we get u dv. Then we get uv, which is normal, then minus v du. Oh, integral v du. All right, so it's going to be, so the formula altogether is the integral of u dv is equal to u times v minus the integral of v du. That's pretty clever. When did they come up with that? Brooke Taylor. Oh wow. I feel like I never hear this name. You hear about Taylor all the time, but you don't I don't know. I didn't know his name was Brooke. Kind of weird. Anyways. Okay, so now that was actually very insightful. All right, so let's do this example. The integral of x sine x. Okay, suppose we took f of x equal to x, g prime of x equal to sine. All right, so so f of x is equal to x, g of x is equal to minus cos of x. So then dg dx is equal to sine. And so then you have dg over sine is equal to dx. So then if you replace it, you're going to get the integral of x dv, which is really dg, which is times sine x u times sine x times dg over what? Okay. Wait, what's formula 2? U is equal to x, du is equal to dx, dv is equal to sine x dx. Then you integrate both sides, you get v is equal to minus cos x. Okay. And you just plug in. I like this formula. This one's nice. I definitely want a bunch of practice with this. Because once I do the practice, then I'm... Yeah, so the first steps are you figure out what u is. So integral of ln of x dx. We're going to say u is equal to ln of x. So then du is equal to, 1 over x dx. Then we let v dv equal dx. So then v is equal to x. And then once you have those four things, you can just figure out that integral of u dv is equal to uv minus integral of v du. So then you can just so then you get uv is ln of x times x minus the integral v, which is x times 1 over x dx. So that's just going to be x. So it's x ln x minus x plus c. Okay. Oh, no. Right, yeah, these iterated integration by parts where you do it until it dies. That's pretty crazy, actually. Wow. All right, so I guess I do want some practice with those ones. Oops. When do you integrate by parts and when do you not? Let's see, how long have I been practicing? 2 hours and 20 minutes. Oh. Okay. Let's do two of them, and then I'm gonna eat some food, and then after this, um, what's happening? I think I think maybe it's just more of this. I mean, yeah. So I'm gonna make some food, and then we're gonna do a bunch more of all of this stuff. Oh yeah, partial fractions. I forgot about that. Okay, so that was the first part of the integral calculus review.